Chapter 12. An important environment/health study involved children who lived within 7 kilometers, or about 4 miles, of a large ore smelter in El Paso, Texas. Because the smelter emitted lead pollution, there was a concern that these children would somehow suffer. The focus on this chapter problem is to investigate the possible effect of lead exposure on performance IQ scores, as measured by the Wechsler Intelligence Scale. Based on measured blood levels, the children were partitioned into a low-level group, a medium-level group, or a high lead level group. And back in this first Excel lab, what we did was we compared the low blood level group and the high blood lead level group. And so we did this in our section on comparing two means. So we compared the mean of this low lead level group to the high lead level group. And so this did a sufficient job of determining if there was a difference between the mean IQ for those who weren't that exposed and the mean IQ for those that were very exposed. But there's another thing we want to look at, because if we can only compare two means, then we're completely leaving out this medium blood lead level group. And so what if we want to compare all three means? That might give us a better idea of the effect of exposure on children's IQ. And we could compare the mean from the low level, the mean from the medium level, then we could compare the mean from the medium and high level, and then finally we could compare the mean of the low and the high level. So we could do 3 tests comparing the two means. So 3 two-sample t-tests, since we don't know the population standard deviation. But there's a problem with this. Now the first problem isn't really a problem, it's more of an inconvenience, that if we're doing 3 two-sample t-tests, it's just a little bit more time consuming for more samples. The other problem is an actual problem, and this is what's called the buildup of type 1 error. Because let's remember that a type 1 error is what happens when we reject a true null hypothesis. And we know that our level of significance alpha is just the probability of a type 1 error. And so I know that probability and confidence level are related. I know that confidence level is just 1 minus alpha. Okay, and let's say I'm performing an experiment with a 95% confidence level. And I'm saying that when I'm comparing mean 1 and mean 2, so this is my null hypothesis for this first test. I'm comparing mean 1 and mean 2. I have a confidence level of 0.95. Meaning I have an alpha of 0.05, pretty standard. Well, that also means that if I'm comparing means 2 and 3, then I also have a confidence level of 0.95 with that level of significance of 0.05. Okay, and now if I'm comparing mean 1 with mean 3, again, confidence level of 0.95. Now if I think of this crudely, that I have a 95% chance that I won't have a type 1 error in each of these 3 cases, then what's the probability that all of these events will occur? In other words, what is the probability that there will be no type 1 error in all 3 experiments if they are performed simultaneously? Well, let's remember back to statistics 1, when we talked about basic probability. If I want to find the probability of event A and event B occurring, and they're independent events, then I'm going to take the probability of A and multiply this by the probability of event B. And so the same logic applies here. And so to find the probability of no type 1 error, I'm going to take the probability of the first event, so 0.95, and multiply it by the probability of the second and third event. And if I multiply these values, I get 0.85, let's round, 0.857. Now, if this is the probability that there is no type 1 error, what that means is I'm left, this is my confidence level of all three of these events, and with a confidence level of 0.857, I now have an alpha of 1 minus this value, so that's going to be 0.143. This is a very high alpha. And so this won't really make a good experiment. This means that we're going to have a much higher confidence level for each of these three tests of means to get an alpha of 0.05 for the experiment. And so that's the problem with our previous method. And so that brings us to one-way ANOVA testing. In this section, we're introducing this method of one-way analysis of variance, and this is abbreviated ANOVA, which is used for tests of hypotheses that three or more populations have means that are all equal. Now, there's really no cap in this. Generally, we don't have too many populations that we're comparing, but we can use this for an unlimited number of populations. If we are testing the hypothesis that three or more population means are all equal, that means that our null hypothesis is that of equality, and that's that mean 1 is equal to mean 2, which is equal to mean 3, so that all three of these means are equal. The calculations here are a little bit complicated, and so we are going to just emphasize the interpretation of results obtained by using technology. We're just going to use technology. The methods of analysis of variance require the F distribution, and the F distribution has the following properties. Number 1, it's skewed right and is right-tailed. If it is right-tailed, that means it's going to look something like this. It's going to have a long right tail. Values cannot be negative. We can see I've just drawn only the positive values starting at 0. The exact shape depends on 2 different degrees of freedom. You can see that this looks a lot like a chi-square distribution. In our chi-squared distribution, we know we have a table for this, and we know that this just depended on our degrees of freedom and our confidence level. And let's look back at that table. So in this table, we've got the standard confidence levels and some kind of standard degrees of freedom. You can see that we start skipping up near 100. The problem now is that if we're depending on 2 different degrees of freedom, where the first degree of freedom is the number of categories and the second is the difference between the number of samples in the experiment and the number of categories, well, we're going to need a whole lot of tables, and so we're just going to find this critical F value by using technology. So we're always going to use technology to find the critical F value. In one-way analysis of variance, data is categorized with one factor or treatment. So there's one characteristic used to separate the sample data into different categories. Now we can still have essentially an unlimited number of different categories, but there's only one treatment. And if we go back to this example, we can see that there are 3 different categories, low, medium, and high blood lead level, but there's only one treatment, and that's just the lead level, the blood lead level of these individuals. And to perform this type of experiment, again, we're testing the equality of 3 or more population means. We have the requirements that the populations have distributions that are approximately normal. This is a pretty standard requirement. We also have that the populations have variances that are not too different. Now, when we say not too different, this is a very loose requirement, but in general, we know that variance just means the average difference of each of the values from the mean. And so if in one of our treatment categories, we have values that are all very similar. In another treatment category, we have values that have just gone absolutely haywire. We know that this might not be the best test to use, but there's really no checking that the population variances aren't too different. There's no formal test for that. We also need the samples to be simple, random, and independent of each other, so these samples are independent. They're not matched in any way. And finally, we have that different samples are from populations that are categorized in only one way, and this just comes from the one-way analysis of variance. Now for our test statistic for one-way ANOVA, because we're using the F distribution, this is naturally going to be an F test statistic. And we're comparing the variance between samples and the variance within samples. Let's think about it this way. If my variance within samples is pretty small, so if I have data in 3 different categories, and all of the values in category 1 are pretty much the same, all of the values in category 2 are pretty much the same, and all the values in category 3 are pretty much the same, they're very similar, then I'm going to have a small denominator. If the variance between samples, if the average of sample 1 is different from the average of sample 2 and the average of sample 3, between samples, if I have more variation, I'm going to have a higher F statistic. And when I have a larger F statistic, that means that this F value is very off to the right, which means I have a small p-value, a small area to the right of that F statistic. And that means that I'm rejecting the equality of population means. If I reject the equality of population means, what I'm saying is at least one sample mean is very different. And this is important here. So if my null hypothesis is that all of my sample means are the same or very close, then I don't need all of these sample means to be different to have an alternative hypothesis. All I'm saying is that at least one of these sample means is different. And so this concludes the summary of one-way ANOVA testing.